Welcome back, everybody. This is our third class in JEE mains previous year question series for chapter Dual Nature of Matter and Radiation. Before this video, we have made two videos in this series, and all of those videos are available on our channel's playlist section. We have also started similar series for NEET, so if some of your friends are preparing for NEET, then they can watch those videos also. And if you find them useful, helpful, then do press the like button, share them, subscribe to our channel, and also if you want to donate us something, scan the QR codes in front of your screen. With this, let's start today's video. In the previous one, we covered up to around 21, I think 20, yeah, 23. Question number 23 we have covered up to. And today we will start with 24. Let me adjust this to white so that now, in the given figure shows the few data points of a photoelectric effect experiment for a certain metal. Minimum energy of electron from the surface is. Now, we know that minimum energy will be equal to the work function. So, basically what we have to calculate here, we have to calculate the work function. Now, this graph is between stopping potential and frequency. So, we know already a relation that E times Vs is equal to H times frequency minus phi. This is the photoelectric relation we have. Now, uh, let's substitute Vs is equal to 0. If Vs is equal to 0, then here left side will be 0 and we will get Hf. And that if suppose Vs is 0, then F is F node minus phi. And from this we can write that phi is equal to HF node. Means when stopping potential is 0, at that time work function is basically H times the frequency at that point. Now here on the x-axis stopping potential is 0. The frequency at x-axis which we get from the graph is 5 into 10 raised to the power 14. So we can say that work function will be 6.626 into F node, that is 6.6 10 raised to the power minus 34 into 5 into 10 raised to the power 14, and this will be in joule. So if I convert it into electron volt, then I will get divided by 1.6 into 10 raised to the power minus 9. So this will be 6.626 into 5 divided by 1.6 into 10 raised to power here. This will go on the top and will add into 14, will give us 33. So basically I will have a 10 raised to power minus 1. Now what we can do here now, let us approximate it. So this is suppose 6.5 into 5 divided by 1.5. So this will go on 0.3 and this will be 65 by 3 and basically 2, let us write approximately. So that will be 22 into 10 raised to the power minus 1 approximately, or 2.2 electron volt. That is nearby to the option D here. Now in the next one, photoelectric effect experiment graph is a graph of stopping potential versus reciprocal of the wavelength obtained as shown in the figure. The intensity of incident radiation is increased. So here, if intensity of incident radiation is increased, so what will be the right answer here? Now we know that intensity is basically number of photons per unit area. So if intensity is increased, then number of photons striking per unit area will increase. Now number of photons will increase, that will cause more number of electrons. So number of electrons will also increase, and if number of electrons are increased, so basically we know that photocurrent will increase. So if we see our options, that straight line shift to right, slope of the straight line with more steep, straight line shift to left, graph does not change. So here we are not sure that whether these will happen or not, because only we know that photocurrent will increase and we have to connect photocurrent with these given options. So what we will do, we will try to get this graph from the sum equation. So we know that E times the stopping potential is equal to frequency H times frequency minus work function. Now this can be written as like this, hc by lambda minus phi. So now if I compare, and it is Vs graph, so let us write that Vs is equal to hc by e lambda minus phi by e. Now if, and this can be further written as Vs into hc by e into 1 by lambda minus phi by e. Now this is a straight line equation that y is equal to mx plus c, where y is stopping potential, slope is hc by e, x is 1 by lambda, and constant is phi by e. Now this constant phi by is a constant, we can say, for the same material. For the same material, work function will be constant, and e is the charge of the electron, that is constant. So this is fixed. So we can say this gap is, this intercept is not going to change. Either we increase the intensity or not, because it does not depend upon the number of electrons or photon current. And regarding the slope, slope has h, c, and e. All these are independent constants, so it does not change. They does not change with intensity. So slope is also not going to change. So as mentioned earlier, that straight line shift to right. This line shift to right means, we can say from that, let me draw that. Suppose this is our axis, and as mentioned that line shifts to right. So if line shifts to right, suppose this is the original line, and if it shifts to right, then after shifting it become like this, or even if it shift to left, this become like this. Then due to this shifting, what will happen, that this intercept value of this intercept will change. Here intercept is increase and here intercept is decrease, and we already discussed that intercept is fixed, so it neither going to shift to right, neither going to the left. Now slope of the straight line gets more steep, and we already know that slope is constant here, so slope is not going to change. So only option D is possible, that is graph does not change, is the right answer. So let us move to the next one. When the wavelength of radiation falling on a metal is changed from 500 nanometer to 200 nanometer, maximum kinetic energy for electrons becomes 3 times larger. The work function of the metal is close to, we have to find out. So for photoelectric effect, we know that half of mv square is equal to energy of the photon, that is basically hc by lambda, because we have given energy in terms of wavelength, so we will use wavelength minus the work function. So starting with, and it has to be calculated in electron volt. So initially kinetic energy becomes 3 times, so let us write it as ke, and let us not introduce mass and velocity, because they need not to introduce. So initially kinetic energy was supposed ke, and it was hc is 1240 electron volt nanometer, value of hc, divided by lambda, and initial lambda is 500 nanometer minus 5. Now kinetic energy becomes 3 times, so 3 Ke is equal to 1240 electron volt nanometer divided by 200 nanometer minus 5. Now nanometer on the both sides gets cancelled, this 0 gets cancelled on both sides, and if we divide both of these, what we will get? We will get 3 is equal to, now this will give us 62 or 6.2 minus 5 divided by this term will give us 2.5 approximate. I'm approximating here 2.5, assuming that this is 125 divided by 5, that will give us 2.5 minus 5. Now if I solve it further, this will give us 7.5 minus 3 phi is equal to 6.2 minus 5, and this will give us 1.3 is equal to 2 phi, or phi is equal to 1.3 by 2, that is 0.65 electron volt. That is nearby to option D here. Now let us move ahead. two sources of light emit X-ray of the wavelength 1 nanometer and visible light of 500 nanometer respectively. Both the sources emit light of same power 200 watts. The ratio of number density of the photon of X-ray to the number density of the photon of the visible light of the given wavelength is. Now we know that number of photons emitted is equal to, and these are basically number of photons per second. This is basically power by the energy. So I can write as both have the same power. So N1 by N2 will be basically equal to E2 by E1. Now energy will be Hc. E is H times frequency, and that is Hc by lambda. So E is proportional to 1 by lambda. So H gets cancelled, and I can directly write that it will be lambda 1 by lambda. Now lambda 1 is 1 nanometer. So 1, and both are in nanometer, so nanometer is also cancelled. So this will be 1 by 500. That is option A for us. Moving ahead to the next one. When radiation of wavelength lambda is used to illuminate a metallic surface, the stopping potential is V. When the same surface is illuminated with the radiation of wavelength 3 lambda, stopping potential is V by 4. If the threshold wavelength of the metallic surface is n lambda, the value of n will be. So, from the Einstein's relation, we know that E times Vs is equal to energy of the photon, that is basically Hc by lambda, minus work function phi. So initially we have E into V when stopping potential is V is equal to Hc by lambda minus phi. Then we reduce wavelength to increase wavelength to 3 lambda, and it becomes V by 4. So E times V by 4 is equal to Hc by 3 lambda minus phi. Now if we divide both of these, what we will get? We will get EV divided by EV by 4 is equal to Hc by lambda minus phi divided by Hc by 3 lambda minus phi. Now EV gets cancelled. Here we will have 4 and cross multiplying it. This will give us 4 Hc by 3 lambda minus 4 of phi is equal to Hc by lambda minus phi. Now this can be written as 4 Hc by 3 lambda minus Hc by lambda is equal to 3 phi. Now what I can do to solve it is I can multiply 3 here and 3 here. So this will become Hc by 3 lambda after subtraction is equal to 3 phi, and from this phi is Hc by 9 lambda. Now it is mentioned that threshold wavelength for the metallic surface is n lambda. Now this is the threshold energy, and it has to be equal to Hc by lambda threshold, and if we compare both of these, then lambda threshold is 9 times lambda, and we have to find n, so n will be basically 9 here. With this, let's move to the next one. Radiation of the wavelength 6561 angstrom falls on a metal surface to produce photoelectrons. The electrons are made to enter a uniform magnetic field of 3 into 10 raised to power 4 Tesla. If the radius of the largest circular path followed by the electron is 10 millimeter, the work function of the metal grows to. Now we know the radius here, and for a electron or charged particle moving in circular path, radius is given by mv by qv. So, and this mv is basically momentum. So r is equal to p by qb, and momentum can be further written as under root 2me divided by qb. So from this, what we can do, we can find an expression for energy. So r square into qb, squaring both sides, so q square b square divided by 2m is equal to energy here. And this is also the relation in the cyclotron type, where particle move in a circle, the kinetic energy is given by this relation. So you can use that also directly, or you can use this method to drive it. So value of energy will be radius square, so 10 into 10 raised to power minus 3 square into Q, that is 1.6 10 raised to power minus 19 square into B, that is magnetic field, that will be square of that, so 9 into 10 raised to power minus 8 divided by twice the mass, that is 9.11 10 raised to power minus 31. So when we solve this, what we will get? I have actually already calculated, so it is 0.787. Oh, sorry, as it has to be calculated in joule. So in joule it will be 1.26 10 raised to power minus 19 joule. Now I can convert it into electron volt by dividing 1.6 into 10 raised to power minus 19, and this will be equal to 0.787 electron volt. Now we know that energy is equal to, means kinetic energy of the ejected electron is hc by lambda minus the work function. So here hc by lambda, this is the energy of the incident photon. Kinetic energy, this is the energy of the electron. So this will become 0.787 is equal to hc, that is 1240 electron volt nanometer, divided by the wavelength, that will be 656.1 nanometer, it is in angstrom, and minus 5. So from this 5 can be calculated as nanometer gets cancelled, and this will give us 1.89 electron volt minus 0.787, and this will be equal to 1.10 electron volt, and that is nearest to the option A. So option A will be the right answer for this question. With this, let's move to the next one. When a photon of energy 4 electron volt falls or strikes on the surface of a metal A, ejected photoelectrons have maximum kinetic energy Ta, d Broglie waves lambda A. Maximum kinetic energy photon liberated from another metal B give by a photon of 4.5 electron volt is Ta minus 1.5. If the de Broglie wavelength of the photon is twice the lambda A, the work function of the metal B, we have to calculate it. So this question is slightly, means it has two parts and both of these are connected to each other. So let's start. Now kinetic energy, let's say Ta, this is the kinetic energy of the ejected electron, that will be equal to the energy of the incident radiation, that is 4, minus the work function for the first metal, that is suppose phi A. Similarly, kinetic energy for the second one, that is Tb, that will be equal to energy of the incident electron, that is 4.5, minus the work function, that is phi b. Now it is given that Ta is equal to, oh sorry, Tb is equal to Ta minus 1.5. So what we can do here, we can form a relation by substituting it here. So Ta minus 1.5 is equal to 4.5 minus 5p, and from this what we will get, we will get phi of b is equal to 4.5 minus Ta and plus 1.5, I think. So from that phi b will be equal to 4.5 plus 1.5, that is basically 6 minus Ta. So now come to the wavelength terms. It is mentioned that de Broglie wavelength or lambda b is equal to twice of lambda a. Now lambda we know that is basic, this is de Broglie wavelength, it is h by the momentum, and that will be h by the under root 2m times E, where E is the energy of the electron, because this is the de Broglie wavelength. De Broglie wavelength is mainly of the particles. Only particles have de Broglie wavelength. So this de Broglie wavelength here will be for the electrons. and this energy E is of the electrons, and this energy Ta and Tb are also the energy of the maximum energy of the ejected electrons. So we can write that lambda is equal to h by 2m into T. Now lambda b will be h by 2mTb under root, and here lambda a will be h by under root 2mTA. H gets cancelled as electrons are same, so 2m will be get cancelled, and from this we have a relation between T and Tb. Squaring both sides, we will get 1 by Tb is equal to 4 by Ta. So what I can do here from this, that mm, T of A is 4 times Tb. Now I think I can use this relation. Yeah, I can use this relation here. That Tb, if I use this one, that Tb is equal to Ta. That Ta is 4 times Tb minus 1.5. So this from this 1.5 is 3 Tb, and from this Tb is 1.5 by 3, that is basically zero point 0.5. So if Tb is 0.5, then T of A will be 4 into 0.5, that is 2. So we have to find out work function of metal B, and basically we have to find out phi B. This is the relation. So phi B will be 6 minus Ta, and Ta is 2. So 6 minus 2, that is 4 electron volt. So option A will be the right answer. Moving to the next one. A beam of EM radiation of intensity 6.4 into 10 per watt per centimeter square comprised of wavelength lambda 310 nanometer falls normally on a metal plate. One function is given, surface area is given. If 1 in 10 to the power 3 photons ejects an electron, total number of electrons ejected in 1 second is 10 to the power x. So we have to calculate x here. So let's start. As here we have been given intensity. Intensity is given to us, that is 6.4 into 10 raised to power minus 5 watt per centimeter square. Now we know that number of photons striking on the plate per second will be energy, power by the energy of the photon. So what we have to calculate? We have to calculate first power, and we know that relation between power and intensity is basically power by area. So power becomes I times A. So we have the power, and now energy. For energy we need lambda, and energy will be hc by lambda. So number of photons will become the formula for number of photons, that is Ia divided by hc, and we will have lambda here. So I is 6.4 10 raised to power minus 5 area, that is 1 centimeter square, and it is basically in centimeter square. So uh, that we don't have to worry that much regarding unit conversion, that both are in centimeter, so centimeter get cancelled. Hc is 1240, and it is in electron volt. It is given in electron volt. So what we have to do here, we have to convert it into, we can say, joules. So it is 1240 electron volt nanometer. So 10 raised to power minus 9 is there, and we have to convert it into joules. So multiply 1.6 10 raised to power minus 9. And this is Hc. Now multiply the lambda. Lambda is 320 nanometer. Oh, sorry, 310 nanometers. So minus 9. This minus 9 gets cancelled. And basically what we have here, if we multiply this to the 64, so we will get 64 into 10 raised to power minus 5, and adjust this 0 with here. So 124 into 16, and here we have 10 raised to power 19 in the top. So this will go on 4, this will on basically 31. So 1 by 31 into 10 raised to power 14 photons we have per second. And 1 by 31 can be written as like 1 by, this can be written as 100 by 31 into 10 raised to power 12. Now it is mentioned, okay, correction here, I forgot 310. I forgot here 310. So here in multiplication I will have 310. So 310 will also be here and this will get cancelled. I think, okay, let me redo this whole scenario because there is a mistake. So let me redo this. So this 10 gets multiplied with 6.4, so it becomes 64. And I have 10 raised to power minus 5 here and 310. So 310 and 10 raised to power minus 5. Now in divide, I have 124 because its 0 is multiplied with 1.6. So 124 into 60 and into 10 raised to power minus 19 here. So this is the basic setup. So this will go on 4, this will go on 31 and this will go on 10. So what I will get? I will get 10 into 10 raised to power minus 14 plus 14. So this is basically 10 raised to power 15. And I am getting 1 electron for 10 raised to power 3 photons. So number of electron will be, that is 10 raised to power 15 by 10 raised to power 3, that will be 10 raised to power 12. So X here will be, that will be 12. Oh, sorry, one more mistake. That I took area 10 centimeter and actual area is 1 centimeter. So what I have to do, I have to divide here by 10. So 1 by 10 also will be there and 1 by 10. So this will be 10 raised to power 14 actually. And if it is 14, then this will be 12, 11. So actually 11 will be the right answer, not 12, because I took area as 10. I think I was writing something else and it go to right 10. So I have to divide it by 1 by 10. So answer will be 10 raised to power 11 and x will be 11. Moving to the next one. The stopping potential in volts as a function of frequency for a sodium emitter is shown in the figure. The work function of the sodium from the data plotted in the figure will be. So basically we have to calculate work function here and we have graph between stopping potential and frequency. Now we have the relation between the stopping potential and energy from the Einstein's photoelectric relation, that EVS is equal to energy, that is H type HF minus phi. Now as graph between is between V node and frequency, so we can write that Vs will be equal to H by E times frequency minus phi by E. So this will be equal to slope and this will be equal to the intercept. So here this intercept is along y-axis and the value of intercept along y-axis is not provided here. Intercept only provided along x-axis. So what we will do, we can use another trick, that when we know or V stopping potential is zero, when stopping potential is zero, if we substitute here stopping potential 0, then what we will get? We will get E into 0 is equal to HF minus phi, and from that HF is equal to phi. Now when stopping potential is 0 at this line, horizontal line, we have frequency as 4 into 10 raised to power 14 hertz. So phi will be H, that is 6.26 10 raised to power minus 34 into frequency, that is 4 into 10 raised to power 14, and this will be in joule. So and answers are given in electron volt, so that will be 1.6 into 10 raised to power minus 19 of electron volt. When we solve this, we will get 1.65 electron volt, that is nearest to the option B. So option B will be the right answer here. So in a photoelectric experiment, the threshold wavelength of light is 380 nanometer. Wavelength of incident light is 260 nanometer. Maximum kinetic energy will be. So here threshold means that related to work function. So we can write that kinetic energy maximum will be equal to hc by lambda incident minus work function, and work function will be here hc by lambda naught. So Hc is 1240 electron volt nanometer divided by the incident, that is 260 nanometer, minus for work function it will be 1240 electron volt nanometer divided by 380 nanometer. So nanometer gets cancelled from both of these, 0 gets cancelled, and what we will get from here, we will get 62 by 13. So this will be approximately 5 from this, minus, that is 128 4 by 38, so this will be 62 by 90, and this will be approximately equal to 2, oh sorry 3, this will be approximately equal to 3. So 5 minus 3, 2, that should our answer should be nearby 2 electron volt. And if you do the exact calculation, then it will be matched to 1.5 electron volt, because to save time we are approximating. So a 2 milliwatt laser operates at a wavelength of 500 nanometer. The number of photons will be emitted per second is, so number of photons emitted per seconds are power divided by the energy of the photon. So power is 2 milliwatts, so 2 into 10 to the power minus 3 divided by energy, and that will be hc by lambda, because energy of a photon is equal to hc by lambda. So that will be 6.626 10 to the power minus 34 into C, that is 3 into 10 to the power 8, and here we will get lambda that is 500 nanometer. So 5 into 10 to the power minus 9. So this will give us 1000, and that will cancel 10 to the power minus 3. So basically we will get 10 to the power minus 9 plus 34, and this is 10 to the power 8, so minus 8 also, and divided by 6.626 into 3. So that will give us 8 plus 9, that will be 17. So 10 is power 17. 34 minus 17 is 17. 6.626 into 3, let's take as 20, because this will be 18 plus 1.8, 19.8. So let us assume as 20. So this can be written as 100 into 10 to the power 15 by 20, and that will be 5 into 10 to the power 15. That is option A for us. Moving to the next one. The electric field of light wave is given by this equation. The light falls on the plate of work function 2 electron volt. The stopping potential of the photoelectron is, and here value for E is given. So first of all, what we have to do, we have to find out lambda here. And lambda can be, how can we find lambda? That standard electric field equation is A cos of kx minus omega t. That will be the standard equation here. So from the k, from this, the k will be 2 pi by 5 into 10 to the power 7. So 2 pi by 5 into 10 to the power minus 7, and then we know k is 2 pi by lambda. So from this, lambda comes out to be 5 into 10 to the power minus 7, and that is in meter. So if I multiply by 3, 10 to the power 3 to minus 3, so this will give us 5000 angstrom. So incident energy using the given formula, this one, it will be 12735, and here it is should be mentioned as electron volt. Yeah, it is mentioned in electron volt here. So electron volt angstrom divided by 5000 angstrom. Angstrom gets cancelled, and basically what we will get, 30 will add a decimal here. So 2.4 7 something. That will be the energy in electron volt. And here work function is 2 electron volts, so maximum kinetic energy will be E minus phi, that will give us 0.47 electron volt, and that matches with option C here. Moving to the next one. When a certain photosensitive surface is illuminated with a monochromatic light of frequency mu, stopping potential is V naught by 2. When the surface illuminated monochromatic light of frequency mu by 2, sorry, stopping potential is V naught. Threshold frequency for the photosensitive emission will be. So we know that E times V as from the photoelectric effect is equal to HF minus phi. So if I use this one, initially frequency is V and stopping potential is V naught by 2. There is no negative. I think it is just typing mistake. So E times V naught by 2 is equal to H nu minus phi. For the second time, it is E times V naught is equal to H nu by 2 minus phi. So what I can do now? Now, if you have observed this rule clearly, then you might encounter a doubt that as frequency increases, what will happen? Energy will increase, and if energy is increasing, it means maximum kinetic energy will increase, and maximum kinetic energy increases, then stopping potential will also increase. And here we can see that when frequency is mu, then stopping potential is V naught by 2. But after that, frequency decreases. Frequency decreases from by half, but stopping potential increases by 2. So this is the reverse behavior, which is not possible. So here I think there is some problem in the question. Either it should be reversed, that it should like that, like this, that E V naught by 2 should be equal to H nu by 2 minus phi, and E V naught is equal to H nu minus phi. So if I use this one and divide both of these, what I will get? I will get 2 is equal to H nu by 2 minus phi by H nu, sorry, 1 by 2 is equal to H nu minus phi. Now cross multiply, H nu minus phi is equal to H nu minus 2 phi. Now H nu and H nu gets cancelled, so still I think there is some problem with the statement. So moving ahead to the next one. In the Frank-Hertz experiment, electron of energy 5.6 electron volt passes through mercury vapor and emerges with an energy 0.7 electron volt. Minimum wavelength of the photon emitted by the mercury atom is close to. Now, as for the statement, what is happening here? That there is an electron that enters into some chamber here with energy of 5.6 electron volt. After it comes out, what happens? That its energy is 0.7 electron volts, means it loses energy. It loses energy, and assuming there is no loss due to heat and some thermal effect, that loss in energy delta E will be 5.6 minus 0.7, and that will be 4.9 electron volt. Now we have to find out minimum wavelength. So minimum wavelength means we have to find out minimum wavelength, minimum lambda means frequency will be maximum. And if frequency is maximum, if maximum frequency is required, means there should be a single transition. Means actually what will be happening here, that suppose this is a mercury atom. When electron is passing by, it will strike to it, and here the electrons of the mercury atom will make excitation or transitions. Now if they make multiple transition, there is possibility of multiple transition, but if there is multiple transition, then we will get low frequency radiation, because that energy 4.9 electron volt is distributed between different radiation. So what we will get, low energy radiation. And if we have low energy radiation means low frequency radiation, and if frequency is low means high wavelength radiation. But as per the requirement we need low wavelength. So if means low wavelength means high frequency, and high frequency is only possible when we don't have the multiple radiation, we have only single transition. So for single transition we can write that E is equal to hc by lambda, and from that lambda is hc by E, and that will be hc is 1240 electron volt nanometer divided by E, that is 4.9 electron volt, assuming it to be 5. So we can approximate 1240 by 5 nanometer. So this will be 248 nanometer. That is nearest to option D for us. So with this, I end this video here. Hopefully whatever I have covered here is helpful to you. Again, if you have any doubts or suggestions, you can put them in comment section. I will try to resolve them. And if you like to donate something or anything, please do donate. It helps a lot to keep these videos and keep the channel alive. With this again, thanks for watching, and we will meet in next video.